Good morning, everyone. This is Mrs. Rondo. This lesson is going to be about corresponding parts of congruent figures are congruent and proofs. So we're going to be using corresponding parts to help us prove that figures are congruent. And so here we have our essential question. How do I write two-column proofs that include CPCFC? And then our learning goal is we're building to triangles. So you're going to see that in our learning goal. Right now, we're going to be working with all different figures, but then we're going to be moving to triangles. So the learning goal is written for triangles. It says, I can prove a pair of triangles are congruent using corresponding pairs of sides and corresponding pairs of angles. So again, proving that two figures are congruent. All right, so your notes are available on Google Classroom. You're welcome to write your own copy. I would probably suggest writing your own copy or using Kami because you're going to want to be able to mark your diagrams. But if you do not have that availability, you can just use the Google Doc. That's fine. All right, so here we go. We're going to be looking at some different definitions and properties before we jump into proofs, because these are going to be our ways that we justify our work. So the first one we have is reflexive property. This one is super important, and it's going to look maybe a little bit silly. Basically, reflexive property says if I have a side or segment AB, that I can say that it's congruent to segment AB or itself. So yes, it does seem a little bit silly, but it is necessary, specifically when we have figures that share a side, like they are drawn so that they have one side that matches up. It's a shared side. We'll see it pop up. So it's a necessary thing. We need a way to account for that. So we can say a side is congruent to itself, and that's called reflexive property. Then we have another one called symmetric property, which is very similar with one small difference. We can take side AB and we can say that it is congruent to side BA. So basically, we're still talking about the same side, but as we learned last week, the order of the letters matters. So sometimes we might need it to match up with the order of the letters being different, being reversed. So this is called symmetric because it matches. If you look from the outside in, A is on the outside, B is in the middle. It's called symmetric. It's like a mirror image. All right, then the last one is called transitive property. And this one is a bit longer. It basically says if I know that AB is congruent to CD, so a totally different side here, and I also know that CD is congruent to EF, then there's a third statement I can make that says, then my AB must also be congruent to EF. So I call this one the sandwich property because of the way that this matches up. So if we look at it in that way, let me grab a different color for a minute. Sorry, I'm going to grab orange. So if we look at the fact that both of these have CD, if we kind of took the outsides and squished the CDs together, since they are the same, you would see that AB and EF are on the outside. So those two also have to be congruent. Again, I call it the sandwich property, but whatever you want to call it, it's basically a chain of reasoning. If this one is congruent to this one, then this one is congruent to that one, then the one we started with and the one we ended with also have to be congruent. All right, so then we have some definitions. And these are not, this is not a full list. This is just a few that we come across pretty regularly. And I would ask you to possibly add to this as you find other definitions. I know there's some that we come across later that have to do with right angles. But for now, angle bisector, this is a line or segment that splits an angle into two congruent angles. Or we might call this, you'll hear me refer to this as equal pieces. So an angle bisector is a line or a segment that splits an angle into two congruent angles, or two congruent or equal pieces. Then we have a segment bisector. This is still a line or a segment. That splits, and this time because it's a segment bisector, instead of splitting an angle, we're going to be splitting a segment. So it's almost the same definition as above, just the thing that we're splitting into parts is different. So a line or a segment that splits a segment into two congruent segments, or we might say two equal pieces. All right, then the last one is midpoint. And this one we kind of probably know intuitively, but I'm going to just give us a quick definition. A midpoint, this is a point that lies the same distance away from two other points. And this is probably not the definition you would have written, but I'm using this specifically because that's how it gets used in proofs. When we talk about midpoint, we're going to be talking about a point that is the same distance away from the endpoints. And so actually I'll make a comment there, endpoints. Typically we're talking about endpoints of a segment. All right, so those are just some references. You can pause here if you need more time to write that down. I'm going to go ahead and go forward. So these specific proofs can be found in your textbook on starting on page 142, and it just goes on to the next page, 143. So we have write a proof for the following. So this is our first introduction into proofs. And so key pieces of information. The first statement we make, always, statement number one, is always going to come from the given. So without doing anything else, I'm going to say triangle ABD is congruent to triangle ACD. Okay. And immediately I'm going to match that up with, again, this is the very first thing I do. The reason is given. That's how we knew that that was true. It was given to us. The other thing that we could automatically write if we were sure how many steps it's going to take, and you can see I have this pre-built, so we know we're going to do it in 3 steps. But normally, if you're writing it from scratch, you wouldn't know how many boxes. And that is that the last statement is always what you're trying to prove. So because I know what I'm trying to prove, and I happen to have 3 boxes, I could put it in immediately. I'm not going to yet, but I just want to point that out. The first box is always the given, and the last box is always what you're trying to prove. All right, so we have statements and reasons. So the statements are what we know to be true, and then the reason how we know it's true. So I'm going to go to my picture, and I'm looking at the 2 triangles I know are congruent, which is going to give me some information. And then I'm trying to prove, actually, I lied to you. I am going to put this in. I'm trying to prove that D is the midpoint of BC. And the reason I'm going to do that is because we need to somehow figure out how we get from the triangles being congruent to D is the midpoint. So if we go to D is the midpoint, what would we have to know to say that D is the midpoint? That's where we go back to those definitions. A midpoint is a point that lies the same distance away from 2 other points, the endpoints of a segment. So if I think about that in the context here, if D is the midpoint, that means it's the same distance from D to B as it is from D to C. Now, I don't actually know this is true. I just wrote it down really quickly because that's what I'm trying to figure out. But if I look at my what I'm given, I know the triangles are congruent. If I look in my triangle statement, I can see that BD has to match up with CD. And that happens to work out pretty conveniently for what I'm trying to prove. So I'm just trying to piece together, how can I find this information? So I marked my diagram as if it was true, but I have to be able to have a way of saying it, not just, well, I want it to be true, so I'm going to say it. If I look back at my congruent statement, I can see that it's true. So my second statement is going to be just that BD is congruent to CD. And remember, the order matters. I matched it from the congruent statement. So the reason that I actually know these are congruent comes from my congruent statement, or what we call CPCFC. Since the triangles are congruent, all of their parts are congruent. So we picked one part of our triangles to say that it's congruent. So that's corresponding parts of congruent figures are congruent. Then I have my final statement, D is the midpoint. The reason I am able to say that is what we talked about, thinking about what it means to be a midpoint, which would be called definition of midpoint. Because D is the same distance away from B and C, it must be the midpoint. All right, let's give the next one a try. So right off the bat, the very first thing I'm going to do before anything else is I'm going to write out my given. So I'm going to abbreviate these fabulous quadrilaterals and say quad, JKLM, is congruent to quad. Hold on, I'm running out of room. I don't like it. Okay, sorry. One more time. Here we go. We have quad. I'm going to squeeze this in a little better. Quadrilateral, let's see, JKLM is congruent to quadrilateral NPQR. Okay, and right off the bat, we know the reason is given. And this one, there are two statements in the given. So there's the original quadrilateral. There's also this one hanging off the back. So I'm going to make that a separate statement. Still going to include it right at the beginning here. That that angle J is congruent to angle K. So I'm going to include it right at the beginning, but I'm going to write them as separate statements because they are separate ideas. All right, and then my reason is still the same. It was given. Then I could even be super fancy here because I have 4 steps laid out. We would know the last one has to say angle J is congruent to angle P. We do not yet know the reason. Okay, but that's what we're working for. All right, so I'm going to go back to what I wrote. Quadrilateral JKLM is congruent to quadrilateral NPQR. So one thing I know that means automatically, since I'm saying they're congruent, is all the parts are congruent. And so the next one tells me that angle J, I'm going to mark it, is congruent to angle K. All right, so angle J is congruent to angle K. All right, if I look at, I mentioned all the parts have to be congruent. If I look at my congruent statement, J lines up with N in the other figure. So I would also know that J and N are congruent, but I don't think that's going to help me get to P. I'm trying to figure out how to get to J is congruent to P. So I could check the next one. I have K from my congruent statement is congruent to P. So K and P, I can maybe do something with that. Let's see. If I say angle K is congruent to angle P, how would I know that? Well, I stole that from my congruence statement. So that would mean I'm doing corresponding parts of congruent figures are congruent. And I can mark that K is congruent to P. That's because they're matchy-matchy letters in the congruent statement. Then I have a lot of J's and K's and P's. If I look at the statement 2 and statement 3, so right here, statement 2 and statement 3, I have starting J is congruent to K, and K is congruent to P. So this is that sandwich property. I start with J connects to K connects to P. If I squish the K's together, I end up with J is congruent to P. And we call that the sandwich property, or in math words, the transitive property. So the reason I can say J is congruent to P is by the transitive property. All right, let's try the next one. Write the following proof. Again, we're going to immediately start with the given statement. Triangle SVT is congruent to triangle SWT. And the reason is given. The other thing I could immediately jump to, again, if I already know how many steps it's supposed to take, I know the last step will be what I'm trying to prove. So segment ST bisects angle VSW. Okay, so let's see if we can figure this out. Once again, we're told right away that the triangles are congruent. So then one thing we know is that all their parts are congruent. If I look at what I'm trying to prove, I'm trying to prove that ST bisects an angle. The angle we're looking at is VSW, which is this whole angle right here. We're trying to show that it's being cut into two equal pieces, so two equal parts. All right, so and remember, that comes from our idea about bisectors. Bisector or bisect means cuts it into two equal parts. So if there was a way for me to say those two smaller angles were congruent, that would be really convenient. If I look at the two smaller angles, I would have VST, and I would have, matching it up, WST. If I try to look at my congruent statement, I did VST, then my order would have to match in the other one. Let's see if it does. WST. It does. Since the order matches up, those angles have to be matchy-matchy, okay? Because we are told those triangles are congruent, those smaller angles would have to be congruent. So I would say angle VST is congruent to angle WST. And my reason is CPCFC. Corresponding parts of congruent figures are congruent. Because we know the triangles are congruent, we know those smaller angles are congruent. Then my last statement that says ST cuts the bigger angle into two equal pieces, we know that because the two pieces are already congruent, what we just talked about, then that falls into our definition of bisector. Angle bisector. If the pieces are congruent, then the angle has been bisected. Definition of bisector. All right, this one is our last one. Again, we're going to jump right into the given statement. So this one again has two parts, so I'm going to split that into two statements. So I have quadrilateral ABCD is congruent to quadrilateral. Oopsie, hello. If I could spell quadrilateral, that would be fantastic. Come on. Okay, being silly. Great. Okay. E, F, G, H. Okay, so that is my, again, given. Always start with the given. And this one, because we have two parts to our given, I'm going to write my two statements. AD is congruent to CD. And that's my given. And then again, because it's preset, I already see how many steps I'm supposedly going to take. So I'm going to put my final statement here at the bottom. This is what I am hoping to prove. I do not yet know how I'm going to do that. Okay, so I start with the quadrilaterals are congruent, which again, as soon as you know the quadrilaterals are congruent, you know all the parts are congruent. Then we're told AD, so I'm going to mark this. AD is congruent to CD. So that piece and that piece within one figure are congruent, and that is given. Now my goal, I have AD in my answer, but I don't care about CD for the answer. I care about GH. So I'm wondering if there's a way I can connect to GH. So if I look at my congruent statement, I see GH and I see that matches up with CD. So I could write a statement that says, okay, CD is congruent to GH based on the congruent statement. And I would mark it, CD is congruent to GH. And notice the order of the letters CD, C to D, and G to H. They always have to matchy-matchy. Okay, so then if I look, the reason that I knew that was my corresponding parts of congruent figures are congruent, CPCFC. If I just look at my diagram, then you should be able to see by how it's marked, because I had to match GH to the CD marking, so one tick mark each. You can see just by the marking that AD has to be congruent to GH because of how it's marked. But the way we would give that reason in our proof is actually one more time that sandwich property. I started with AD, I went to CD, then CD matched up with GH, so the ends or the outside of the sandwich is congruent as well. So my last statement here would be because of the transitive property, which I call the sandwich property. And that is it for our notes. Thank you guys so much. Have a great day. Make sure to check out the homework.